I'm feeling a little bit under pressure right now because this is the worst timing ever to discuss any complex topics like quantum computing after lunch. And also discussing quantum computing after lunch and when we got to start from quantum mechanics. So try to imagine, try to become in my shoes and figure it out how tough it can be. But let's try. First of all, I want to destroy your confidence about your computing skills and computing power of your systems. First of all, everything what you know about the calculation, computing power is wrong. It means we exactly do not know what is the power of our future systems because we are still using old approach, old paradigm of calculations. We're still using bits and bytes, so 0 and 1s. I know this is a big hole and I love to have the contact with the people, but I have a question for you. If there will be no answer from your side, I will answer it for sure. So, do you know what is it? It's a molecule, yes. It's a very complex molecule. And actually, the molecule is caffeine. And if we will try to simulate that molecule, we got to use the power of 10,000 supercomputers to simulate behavior of this molecule. I think it is quite difficult, first of all, to find that big number of supercomputers which will help us to do that. That's why in the classical world, we need to go to a little bit simplification of our problem. But if we will change the paradigm, if we will change the approach, we can easily make this molecule be calculated using only 160 something which is called qubits. What the qubit is, I will tell you a little bit later. But first of all, the motivation of quantum computing. I'm pretty sure you know that very well. First of all, it's about the world, how the world is built, from what kind of components is built. So, atoms, particles. So, actually, the word is not classical. The word is quantum. So if you want to do the simulation of the quantum behaviors, you need to build the quantum computer which can help you with that kind of simulations. So this is the sentence from my favorite scientist, Richard Feynman, who is the father of modern quantum computing. And as you can see, he said even very strong words like, damn it, the word is not classical. We will not be able to simulate this word using the classical approach, the classical paradigm. What kind of and what type of problems we can solve using the quantum computer? First of all, we are trying to solve all the hard problems, all the problems which are extremely difficult to be solved by classical computers. Because we can solve many things in the classical computers, but the time for calculation will be huge. If we will add just a single problem to it, it will extend exponentially. So that's why we need to change that. You can see there are three different points on this graph. First one is factoring. Are you familiar what the factoring is? All the keys are actually based on the factoring, which is multiplication of numbers. And the factoring is, I have a big number, and I can divide it to the two numbers, which actually are multiplied to have this number. All the encryption paradigms using the factorization. Second one is, of course, quantum mechanics. So all the simulations which are done on the medicine, all the new pharmaceutical companies can be run on the quantum computing. And our goal as a company is to, first of all, create a machine which is capable to make that kind of calculation, but also to be able to show that that kind of approach is much, much faster than classical. As I can see, it is called quantum advantage. And that kind of quantum advantage were already shown by IBM research in 2018. Where we see the place for a quantum, where it can help to create or to build advantage around this area. So first of all is a quantum chemistry, and so quantum simulation. Second one is artificial intelligence. So everything which is related with speeding up the machine learning process, speeding up the AI around the calculations will be quite good point where we can use the quantum calculations. Fraud detection, pattern matching, and so on. Those things are NP problems, so non-polynomial problems, where quantum is for sure perfect match. Again, for industries like banking and everything which is related with the banking, with the risk analysis, the Monte Carlo method is used to calculate that kind of risk. And of course, using the quantum approach, we can speed it up exponentially. So what do we need to know to be familiar with the quantum computing? So those are the words which actually will every single time appear when we will discuss the quantum world, like entanglement, like coherence, algorithms, like Dodge, Groover, Shor algorithms, and so on, so on. Those information are key points for the quantum, but let's make it simple. Let's change our thinking to be more quantum-like. So on the left side, you can see the bits, so 0 and 1. In the quantum world, we are talking about the qubits. So this is the state between 0 and 1. So the qubit at the same moment can be 0 and 1. And we can decide what is the amount of the zeros and the amount of the ones. How to describe it easier? Okay, I have a coin, which is a perfect bit. Because if I will lay down the coin on my hand like this, it has 1 or 0. Easy. And the qubit actually is something like this. You are spinning the state. Is the coin perfect qubit? No, because you can see it can just stay in this time for a couple of seconds, even less. And I don't have any possibilities to control of the movement and spin of this coin. And try to imagine that you have a particle which is in the system which is capable to control this spinning coin and make the calculation around that. But it's not even half of the power of the quantum computing. Let's see how it looks if you have a single coin. So we have two states. It is state 0 and the state 1. A and B are just the probabilities of those states. If we will add one more qubit to the system, we will have 4 states. So you can see 0, 0, 0, 1, 0, 1, 0, and 1, 1. If we will add one more, we have 8 states, 0, and so on. 8 basic states. And the question is it similar what do we have in the classical world? Answer is yes. So where is the power of quantum computing? The power is in the moment where you can have all those states for the system in this moment. For the classical computer, you can have all of those states, but only one per moment. So you can have a system who has 3 zeros. That's it. In the quantum world, you can have all of them at the same moment. And try to figure it out if we have the possibility to use that kind of calculation, how can easily speed up the calculation process exponentially, just adding one more qubit. If we will just go to n qubit system, we have n basic states. Last year, IBM showed on the audience, announced the quantum computer which has 50 qubits. Okay, 50 qubits doesn't look very big system, but if you will see the number, it is 1 quadrillion states possible at one moment. Next step can be system with 275, which is bigger than number of atoms on Earth. So actually, you can see in the 2 years of the history of the device in IBM, we have jumped from 4 qubits to 50 qubits. So you can see how fast is adoption of quantum computing. I mentioned about the superposition. The superposition is just the dropping the coin and this rotating. When I grab the coin, the possibility to be on state 1 or 0 is 50-50. Yes? If I have a possibility to connect 2 coins and just throw it into air, both of them, and create a connection between first coin and the second coin, we will have something like a phenomena which is called entanglement, which is a devil phenomena according to Einstein. So we will know the exact states of the both connected qubits, but we do not know the states of the single one. It will even give us much power into that kind of system. But of course, nothing is simple in the quantum mechanic world. So that's why you have different approaches. You have different quantum computers. So first one is a quantum annealer, which can do kind of simple calculations, but it's not feasible to do any advanced circuits. Next one is approximate quantum computer. The problem of the computer, that kind of, is we have only physical qubits, and the error mitigation is something as a must to make those calculations directly and make those calculations to give you the right number. And the last one is a holy grail of the quantum world, is universal quantum computer. What does it mean? It means the system has 1,000 qubits, but those are the logical qubits. So to mitigate the errors inside the system, every single logical qubit will contain 1,000 or 10,000 physical qubits. So you can imagine right now where we are in this world. We have a system with 50, 100, 150 qubits. You can see what is the distance for us to be reached the quantum advantage. The main issue with the problem, like I said, it's not just the number of qubits, but also how the coherence, how the hardware gate set, how the connectivity will work. So we need to mitigate the error rate to make the calculation volume higher, bigger. You can see, I'm just adding additional qubits. I have 500, but the volume doesn't change at all. So we need to mitigate the errors. We need to show the difference between that kind of systems. OK, let's play a little bit. How does it work with the qubits? How many qubits do we need to fulfill some calculations, to run some calculations? So if we will just do quantum chemistry, we can do the easy simulations just using 10 qubits. We can simulate the molecules like beryllium, like lithium, for example. We can easily solve that kind of molecules. So next one is optimization, which is also for us quite important point. We need to create the optimization systems and the optimization calculations to go for the business to help them to solve all the risk problems. You can see here, again, we can use these quantum computers which we have right now, but it requires around 100 or 1,000 qubits. 5 years, I would say right now we are able to calculate that kind of problems. And also we can support the AI and machine learning with a quantum computer. We have the algorithm which is ready to be used in that kind of environment. If you will check the Shor's algorithm, so for this one, to make the calculations like factorization, for example, let's say to break all the keys, this is the number of qubits which we need, and we need the fault-tolerant qubit to be able to calculate that kind of hash, for example. So we can see how far, what is the future for the quantum computing. But to be able to think, to be able to calculate, to be able to use quantum computer, you don't need to be a quantum mechanics scientist. You can actually turn on your phone and you can try to find easy application which is called Hello Quantum from IBM, where you can play the circuits, you can play with the gates, and you can actually create the circuits inside the game. And became familiar with how the rotation works, what kind of qubits are you using, and so on. But the most important part is you have an access to the quantum device, which is located in IBM Cloud, and you can run your algorithms on this system right now, even from the phone. If you will open your browser, just type IBM Q Experience, you will have an access to Composer when you can compose your algorithms. So it's quite simple. Yeah, but it only looks simple on the picture. The real system looks like this. We have the microwave electronics, which is controlling the qubits. We are using the superconducting qubits, which you can see it's over here. Here is the chip of the qubits and the resonators. The qubit is the square part, and here is the resonator. So we are controlling the qubits from the microwave electronics through this wire, through this resonator, and then we are able to put the superconducting circuits into the state of 0, 1, or superposition and run the algorithm on that. The important part and the difficult part is keeping the system cool, keeping the system far away from errors. So this is we call it chandelier. This is the system for IBM Q4 with the 4 qubits, like this one. And you can see the circuit is over here. The whole chamber is around 1 meter long. On top of this, you have 40 kelvins. At the bottom, at the very bottom, you have 0.015 kelvins. So almost 0 kelvins. The temperature of space is around this, here, 2 kelvins. So as you can see, how difficult it is to get the quantum system, quantum circuits, to behave like we want, to run the algorithms on that. How it works from the perspective of programming. First of all, we have the machine when we are building the quantum circuits. Then we are sending the signal into electronics, which is changing the frequency of the wavegates, and it's reaching the qubit. It's setting up the state, and then you are reading back the information. The key point of this process is when you are doing the calculation, and here you have the result. When you are running the calculations and you are doing the math, you are changing the states of the qubits. You are rotating the qubit around the Bloch sphere. So this is just a pure vector game. And you are rotating this one across all the axes. The main problem, actually it's not a problem, it's a quantum world. If you will make the calculations around the Bloch sphere, and you want to read back the information from the qubit state, you need to destroy the qubit state to put it as a 0 or 1. So everything which you are doing with the qubit, when the qubit rotates, must finalize on the 1 state at the end, because we need to go to the classical register to have zeros and ones. Quite important part around the quantum computing is not just having the hardware, but also is having the full picture and full scope around the quantum computing. So you can see here, first of all, you're requiring to have a hardware, so device. Then you need to have possibility to access to the device, like a cloud, like network, like a connection from your classical computer into the quantum computer, so the backend over here. But also, you need something which is called Aqua, which are the libraries for your programmers, for your developers, to be able to create, to use quantum computer. It's quite funny, because you can use the library, library written for you, without even knowing anything about quantum mechanics, and you will be able to run the algorithms to create your own script for optimization, for AI, for quantum chemistry. This is ready to go. Third part, like R and Ignis. R is a part when we are delivering your simulators. So not all the algorithms must run on the quantum machine, because it is making a cost. You need some time to run the script. You need to wait in the queue for a quantum device. But if you want to just test your ideas, you can use the simulator. And the fourth is the Ignis. And the fourth element is the Ignis. The Ignis is responsible for mitigating errors. So as you can see, we have 4 elements, like Aqua, Ignis, Terra, and Air. So you see, this is the full picture which you have and which you got to have to run in the efficient way that kind of calculations. If you have possibility to access, here is the composer. You can see how the composer looks like. I think on next slide I have a bigger picture. But you can see 100,000 users till now run the experiments on this real device. Actually, we are capable to deliver access to the quantum machine on 7 continents, doesn't matter where. This is the number of experiments and the paper written around IBM Q. But the quite funny part and most interesting is the KISS kit. It's the software information kit which allows you to use the quantum device from open source, from high-level languages, and use it for free for education, for your project, or even for industry which you are working with. How the composer looks like is quite simple. We can see here. Here is the quantum register. All the qubits at the beginning are set to 0. And then we are running the experiment. We are putting the gates. The gates are usually just the rotations. And then at the end, everything goes down into the classical register to have the information. It's a 0 or 1. Simple as that. Here is the number of the gates which you can use in the system, but the number of gates, of course, is expanding. This year, IBM delivered first computer, which is called IBM Q System 1. This is the industrial machine. So you can buy the IBM Q system for yourself, for your company. So you can have your own private quantum device ready to be used. So if you have any customers, feel free to sell it. But the most important part is to cooperate. We have big network of partners with whom we are cooperating on different levels. Those can be in academias, those can be industries, but also directly cooperation between research and partners. But for me, most interesting part is this one, like Q members and the Q startups. We are cooperating across Europe in around 150 quantum startups. So as you can see, this is quite new branch in IT. Okay, where we are in the quantum advantage world right now. So this is 2016 launch of IBM Q Experience, so 2 years. And right now we are somewhere over here. So we are still waiting for presenting, for demonstrating of quantum advantage for more than single problems. And I want to finish my lecture about showing you the future of data center. In that kind of data center, you will have quantum devices mixed together with the classical devices. So you will have kind of hybrid approach, because some problems can be solved easily by classical computers, and some problems can be just sent directly to the quantum and solved on the quantum machines with the exponential speedup. And this is the end of my presentation. If you have any questions, just feel free to grab me on the corridor. If you want to have access to the system, just go to IBM Q Experience. Thank you very much.
Thank you very much for your contribution, Piotr. Are there any questions from you? And I've got a question up front. We have our marathon lady running around with the microphone again. Great. Keeping fit. Thank you for your help.
Okay, let's say I'm Kestutis from the digitaldemocracy.io. So let's say I have a password which is encrypted in SHA-256. That's the one nobody can defeat in the last 10 years, no proof in the world. As of today's world, the fastest world supercomputer can decrypt this hash in 10,000 years.
Correct.
What would be your answer for the real practical, despite keeping in mind all the situations, how quicker that will become, like after 5 years, if somehow you would adopt the quantum computer? What would be the actual decryption time?
Yeah, this is I got to use the typical answer for a person who doesn't know exactly the answer. It depends. It depends on how fast we will be able to create the machines which will be capable to address that kind of hash you want to calculate. And the second one, which way the quantum computing world will go. We will go for the universal quantum computer. We got to wait for another 20 years. But we can create we can use these quantum computers which we have right now with the lower mitigation of error. So if we will have around 3,000 qubits physical, is it possible to break that kind of hash in minutes? But still, 5-10 years, that's why we are in a very good place for that, because we are talking about the future, about next 10 years. So this is the time period where I will expect anything interesting around the quantum IT and the breaking that kind of hash and that kind of problem.
Okay. Thank you very much, Piotr.
I will add one thing.
Yes.
The most important part, we have an algorithm who is capable to do that. It's a Shor's algorithm. So we need just the computing power. We need just the qubits. That's it.
Thank you so much for your contribution, and good luck in your future endeavors with the quantum computing.
Thank you very much.
Thank you.